Hello students, welcome to EPG Pathshala. I am Dr. Amarjit Singh from Himachal Pradesh University, Shimla. Today we are going to discuss about a module called Reciprocal Lattice and Structure Factor from the paper Solid State Physics. So students, let's see what we are going to learn in this module. So we have already the idea of X-ray diffraction, and we have seen the diffraction pattern. And if we notice carefully, if we have examined carefully the diffraction pattern, we see that uh, all peaks are not of same intensity. Some peaks are of high intensity, some peaks are of low intensity. And when we index these peaks, we find that uh, indexing from low value of HKL to high value of HKL, all uh, should we say corresponding to each index, peaks are absent in the X-ray diffraction pattern. So why they are absent? So now we are going to learn something new in this objectives, so that we understand why this happens. So the objective is to understand the need for reciprocal lattice to analyze diffraction phenomena. So here we will introduce a concept of reciprocal lattice and see how it helps, and learn the relationship and interatomic planes relationship um, uh, and interatomic planes, and construct the reciprocal lattice corresponding to various lattices, for example BCC, FCC, hexagonal lattice, etc. So first of all, let me introduce the reciprocal space. What is the idea behind reciprocal space? Now we have a clear understanding of a real space, just as we know that when we are walking in a room, we are walking in a real space. When we are drawing something on a paper, that is, we are drawing a line in a real space. So that is the real space, and it has a dimension of length, angstrom, meter, centimeter, anything of the dimension of length. Let us say you inverse the dimension of length now. So it becomes a dimension of 1 upon length. So if you have such a space which has a dimension of inverse of length, that will be called a reciprocal space. So the question is, why do you need such a space? The thing is that in X-ray diffraction measurement, uh, we are measuring intensity as a function of angle theta. So basically that measurement happens in reciprocal space, and why this happens in a reciprocal space, this will be clear to you when we talk about that slide and go there and shows you that basically um, X-ray diffraction is an study of your specimen in reciprocal space. So we are trying to understand the reciprocal space. We already have an idea of a real space. So here in the slide you see a diagram. So this diagram shows an incident X-ray and then a scattered X-ray making an angle 2 theta, and below this these are the dots which are nicely arranged in a regular pattern, and or you can say a lattice, and this also shows a plane. We have drawn two parallel lines connecting these dots, and this is showing a family of plane, and d here is the distance between these two planes. So from the Bragg equation we are trying to understand the reciprocal space. So you see in the above equation it is written 2d sine theta is equal to lambda. We slightly remodel this equation and write it as below. It becomes 1 upon 2d is equal to sine theta upon lambda. So in this equation our lambda is fixed because we are using monochromatic X-ray source, and now this spacing d in a given crystal, that d is fixed for a given family of planes. So the theta will appear depending on what value of d you have. The diffraction peak theta will appear for a given value of d. Now since you have different values of d's in a crystal, so you will have different values of theta, so you have different peaks in them. So you can see that this equation tells us information about the reciprocal space. So when we say 1 upon 2d, So this is inverse of length, because d here has the dimension of length. So this is inverse of length on the left hand side of this equation, and on the right hand side you have sine theta. So in X-ray measurement, we measure intensity as a function of theta or as a function of 2 theta. So when we are mapping the sample, mapping means you are changing your angle and recording the diffraction pattern. So basically you are varying, you are mapping it in reciprocal space. You are probing in which part of the reciprocal space it shows you the peaks, and that particular the pattern of peak is basically a representation of a reciprocal space. That's why we call it a reciprocal space, because it has inverse of the dimension of length, so which is shown here. So that is the idea of this. So you see in this slide, this is more clear. Here we have side by side a real space lattice on the left hand side, the dots, and the reciprocal lattice. So this lattice is in reciprocal space. It means it has a dimension of inverse of length. So reciprocal lattice basically is a construct. You can say it a mathematical construct. We can construct it from the real space lattice, and this helps us understand when we measure, do the measurement. We do the measurement in the reciprocal space and inverse this is formation into the real space. So you can see this is very clear that you have a family of planes which is shown by the parallel lines in the real space lattice, and the spacing between the dots is small as compared to the dots along the lines. I mean to say that if you see this dots in the real space, one of the dimension of this is large and one of this is small. So this is a rectangular cell. This is not a square in 2 dimension. So where you have a larger dimension, so in reciprocal space that dimension becomes small. You can compare the reciprocal lattice on the right hand side, that in reciprocal space the dimension along this two-sided arrow is large. You can see the two-sided arrow here is large, and perpendicular to this two-sided arrow this is small. This situation is reverse to what you see in the reciprocal lattice. So this illustrates that in real space, if the atoms are close by, in reciprocal space they will be far, and if you have a far uh, lattice or far lattice points in real space, in reciprocal space they will be at the smaller distance. So that is how you can correlate between real space lattice and reciprocal space lattice. So reciprocal lattice basically is our construct, is a kind of mathematical construct. It is not a real entity in a sense, but it helps us to analyze the structure more properly and rigorously. So we have invoked this idea of reciprocal lattice. Now you see in this slide we have given a definition to this reciprocal lattice vectors. How do you define them? This is what you find in any standard text. So where it is written A star is equal to 2 pi B cross C upon A dot B cross C, and similarly it is for B star and C star. So here A star, B star, C star means these are reciprocal lattices. And you can see the unit cell on the right hand side where A, B, C, all 3 sides are different here. And you know that A dot B cross C, this is the volume of this cell. So what would be the direction of this reciprocal lattice? So you can see A star have the direction of B cross C, because A dot B cross C it's a volume, it's a scalar quantity. So B cross C means it will have direction perpendicular to both B and C. So that will be the direction of reciprocal lattice vector A. Similarly for B star and C star shown here. So it also depends which angle they have. Let us say for example if all angle are here 90 degree, then A star and A will have the same direction. Similarly B star and B will have the same direction. C and C star will have the same direction, like this. So you can correlate these two real lattices and reciprocal lattices, reciprocal space and atomic form factor. So here I would like to add something more to this reciprocal space. Just like till now we have understood that there is a relation between real space lattice and reciprocal space lattice, but when it comes to scattering, there is something more. The more is that the electromagnetic radiation or X-ray, it scatters from atoms, or basically the electrons in the atom. The electrons interact with this electromagnetic radiation and is scattered. And how these electrons are distributed around the atom, that plays a role in how strongly or how weakly and radiation can be scattered. So that scattering power of an atom is represented in form of something called atomic form factor, and this atomic form factor is defined as the in the equation below. So F naught Q, it means we are talking about that in a reciprocal space. Q is a wave vector transfer, as you can see in this equation, K minus K dash. So basically this uh, atomic form factor is a factor which depends on which type of atom you are using. Suppose you are using sodium, then it will have one form factor, and then you are using copper, it will have another form factor, because the distribution of electron around the atom changes. So that changes the strength of scattering. So first we have to understand the scattering power of an atom. So you can say that atomic form factor is a representation of a scattering power of an atom. So this diagram on the right, it shows basically 2 points in between one atom. It means the scattering from one electron and from the another electron around the atom. So this is in a, you can say, the same phenomena is happening here at the smaller scales. So this distribution of electrons around this atom will affect this scattering. In this slide you can see that earlier we were talking about an atom, and now this is about the molecular form factor, because molecule is a group of atoms, 1 2 3, or there can be many atoms, and how these atoms are arranged, uh, that determines the molecular form factor. So this is written in this equation and summed over J. J is a type of atom you have in a molecule. So you may have different type of atoms. So for a particular type of atom there is a J. Fj is atomic form factor for that atom, and you just add it up in this fashion. So the different atomic form fraction are added up by multiplying a proper phase factor. It is important because when you are talking about interference, so this is the amplitude which you need to talk about, and this molecular form factor is an amplitude. So that tells us how we need to add up this atomic form factor in a given molecule. So as you have seen in the last slides, that we were talking about a, uh, a diffraction or scattering from an electron, then its Fourier transform gives us the atomic form factor. And now if you have a molecule which is a constituent of few atoms, then there is a corresponding form factor for the molecule. And now this molecule is, let us say, basis, and we put it on a particular lattice. So the now the total scattering amplitude is basically a multiple of a structure factor, which is a function of a structure of the system, and molecular form factor, which is shown in this formula. As you can see, that unit cell structure factor multiplied by uh, lattice sum in the molecule. So if Rn are the lattice vectors that define the lattice, and Rj the position of the atoms with respect to any one particular lattice site, then the position of any atom in the crystal is given by Rn plus Rj, as you can see in the diagram. It follows that the scattering amplitude for the crystal factorizes into the product of two terms which are written below here. So here Fj is a atomic form factor once again, and Qrj, so this is a phase factor. It comes because amplitude would meet either in a phase or opposite to the phase or somewhere in between. So that basically determines the total intensity. Now you can see that for the square of this F crystal Q will determine the total intensity. Now it includes several things: atomic form factor, molecular form factor, and unit cell. So that is why the intensities of the peaks which you see in the crystals are different from one to another, because they define a different set of plane, different family of planes. So it change basically a structure factor for that particular plane, a structure factor FKL. Okay, in some of the slides earlier we discussed and we saw that some of the peaks are not appearing in a given diffraction pattern and they are appearing in other. And also it is important to note that intensity of all X-ray diffraction peaks are not same, but some peak have high intensity, other peak have low intensity, and so on. So what is the factor which determines this intensity? Why there is an intensity variation in X-ray diffraction peak? So that is determined by structure factor and also of course form factors. So here that's how the structure factor is defined in this slide. F HKL is equal to summing over I 1 to n Fi e raised to the power 2 pi I H Ui K Vj L Wi. So here HKL are again the Miller indices corresponding to a given plane in a reciprocal space. So this HKL are integers, and Fi here is a atomic form factor. So basically because this summing up is happening with the phase factor with it, it can be this, it can be 0, it can be something some other quantity. So that we shall discuss in some next slides with an example to clarify it further. So you see here we have defined the structure factor like this. This mode of FHKL is equal to amplitude of the wave scattered by all atoms of a unit cell. So we consider a unit cell divided by amplitude of wave scattered by one electron. So this is the ratio, and intensity is basically square of this FHKL. So as we know that FHKL is a scattering amplitude, you need to square it up to get the intensity. Now we will take examples and see one by one how to calculate this structure factor. FHKL of simple cubic lattice. Okay, so here is an example in front of us. Here we have a simple cubic lattice, as you can see on the right hand side, and here we have calculated its structure factor, and the atomic coordinates are shown 0 0 0. So the question here is that though in the diagram you show the 8 atoms at the corner, and we are just talking about the coordinate of one atom, it is because of the reason that in a simple cubic, if you ask a question how many atoms per unit cell exist in a simple cubic lattice, the answer is 1. So there is a 1 atom per unit cell. So now you can fix the origin at that point, and it means its coordinate becomes 0 0 0, and you calculate the structure factor in below using this formula FHKL, and this exponential factor becomes 1 because these are all 0, and you get it F. So this is how for a simple cubic, or this is primitive cell. So here the structure factor is just an atomic form factor. Whatever is the strength of atomic form factor, that is just the structure factor in this particular case. FHKL for body centered cubic. So here we are going to calculate the structure factor of a slightly different structure. It is also a simple cubic structure like earlier one, but there is a one extra atom at the center. So we called it BCC, or body centered cubic, as you can also see in the diagram. So once again, you need to ask a question to yourself that how many atoms per unit cell exist in BCC, and the answer is 2, because one atom, 1/8 of atom come from the all 8 corners, and one atom is there in the center. So we have 2 atoms. So now we, as we can see that we fix the origin at one of the corner of the atom and call it 0 0 0. You can see the coordinate of one atom is 0 0 0, and the coordinate of the next atom is half half half. You can just verify it from the geometry that on x, y and z axis, it exists at half of the distance of the unit of this unit cell or lattice constant, because this is in the middle from all axes. And so basically these are 2 atoms per unit cell. Now you can see that FHKL has the sum of 2 expressions. F is equal to e raised to the power 2 pi I 0. So this is for the first atom, and then for the next one where the coordinate is half half and half, and when you add up you get this lower relation. FHKL is equal to F 1 plus e raised to the power pi I H plus K plus L. So now you can see that when HKL is an even number, so this is a non-zero, or let us say this is twice pi I. When e raised to the power twice pi I, you get something, it's an even number. So this is 1, so 1 plus 1 is equal to 2. You will have a Bragg reflection which is twice the form factor. But interesting thing is when it is odd, H plus K plus L, if this is an odd number, HKL, these are all integers, this can be even and odd. So this time let us say this is odd. So when you have odd, the value of this exponent will be -1, and 1 minus 1. So this becomes a 0. So that is no reflection. So this explains to us that in earlier X-ray diffraction pattern, we have seen that though the planes exist, lattice planes are there, but there is no corresponding X-ray diffraction peak to that family. It is because of this structure factor. So from the structure factor we can understand that how a structure factor becomes 0. It means that contribute to destructive interference completely, and that particular family of plane does not appear in X-ray diffraction pattern. So this is you can see the another example of calculating the X-ray structure factor, and this time the unit cell is again modified. This is FCC unit cell. So now instead of in the center, you have atoms at the faces. And once again you need to ask yourself this question: how many atoms per unit cell are there in the FCC? And you find these are 4 atoms. So you need to find the coordinate of all these 4 atoms. So rule is this, that 1 of course is at the corner, and that you could put at the origin, so it comes 0 0 0, one coordinate is that. And when you want to find out the next atom at the face, that will have coordinate half half and 0, and 0 half half and half 0 half, like this. You can understand, because when atom is on the face, it will have x and y coordinate but not z, and similarly for other faces like this. So you can see that this structure factor has expanded into the formed 4 terms for this corresponding 4 atoms depending on their coordinates, and we get the structure factor like this. Now we can see that either this HKL has to be, either they should be all even or all odd. So in that case, if they are all odd or all even, this above relationship will exist, because then it will come 1 plus 1 plus 1 plus 1, and this will be a 4 time of f. And if that condition is not met, you will see that two of them are coming with positive sign and two of them are coming with negative sign, and they cancel each other and the structure factor becomes 0. So the peaks will exist only for situation when either all all HKL are even or all HKL are odd. So from this X-ray diffraction pattern, and after indexing it, if you see that all patterns are coming either even or odd, then you can understand this is a typical signature of FCC, and you can identify that this is an FCC structure. So students, let us summarize what we have learned in this module. So first of all, we introduced a new concept of reciprocal space, or then reciprocal lattice. So for a given lattice, there is a corresponding reciprocal lattice. The thing is that if you know that there is a real space lattice, then you can calculate using the formulas which we discussed in this module what would be its reciprocal space. You could know that with this particular symmetry or geometry you would get a reciprocal lattice. So why the reciprocal lattice? As we have learned that scanning of X-rays, or should we say theta, is basically it's a mapping of your sample in a reciprocal space. You're mapping your sample in a reciprocal space. So X-ray diffraction pattern what you obtain, this is the reciprocal space mapping. So that is the purpose of defining a reciprocal space. So if you understand a reciprocal space of a particular specimen, of a particular structure, then you can also get back its real space structure by applying this transformation formulas which we have already used. So it is always convenient to know the reciprocal lattice of a particular structure, and then what happens is with the X-ray we can just from the mapping we can understand that okay, this reciprocal lattice belongs to this particular class of crystal structure. And so this is a very I would say a suitable handle for to study the diffraction. Next we talked about the structure factor was measured in a diffraction pattern. Now defining of the structure factor gave us another tool to identify how the peak intensities are basically related with this structure factor. And the structure factor depends on the symmetry of the unit cell. You can see that we had taken an example of simple cubic, BCC and FCC, and for different kind of this symmetry there was a different rule when this structure factor would exist or would it be 0. The structure factor can be 0 for a given combination of HKL. So when for a given combination of HKL the structure factor is 0, that means we will not see any diffraction pattern there, because that particular structure causes a destructive interference from all peaks there, the scattering which is scattered by all the atoms in that unit cell, they result in destructive interference. So basically those peaks are absent in the diffraction patterns, as we have seen with the examples in the slides.